Should we get started, Dennis? Yeah. Okay. For those of you that are here at the moment, welcome. Thanks for joining our webinar today, titled "Optimising Trackbed Renewals with Geosynthetics in Heavy Haul Rail." My name is Matt Golding, and I am joined today by Dennis Reeve from Geotechnology WA, who's going to be co-presenting with me today. I'll briefly introduce myself, and then I'll hand over to Dennis to say hi, and then we can get straight into the presentation. So, as I mentioned, my name is Matt. I'm the mining BDM in Western Australia, with a focus on rail projects and geosynthetics in rail applications. And I've worked with numerous consulting engineers in this space and some rail operators on some decent trackbed renewal projects. So yeah, I've got a little bit of experience that I'd like to share with you guys, and I hope you get something out of it. So Dennis, over to you, mate.
Yeah, hi, I'm Dennis Reeve. I'm Principal Geotechnical Engineer at Geotechnology WA, as Matt had mentioned. We're a niche geotechnical consultancy working in the rail renewals and mine infrastructure sector. We've developed and implemented geotechnical renewal strategies for a number of heavy haul rail providers, where we've developed innovative formation treatments to deal with marginal materials. So, thank you.
Thanks for that, Dennis. Just a quick one before I start my section. Some quick notes, some housekeeping. We do encourage some questions, so if you've got any, leave them in the Q&A section, and then we'll address those at the end of the webinar. Just an FYI, we are recording this, and the presentation will be available on the Geofabrics Academy website in a week's time. So you can look over it again. We can get started now. So I'm just going to briefly go over today's session. It's broken into two parts. We wanted to make this a more of a practical discussion about geosynthetics using rail rather than overly technical, so you guys can better relate this to real life trackbed applications in the field. So I'm going to briefly go over the key geosynthetic products that we typically use in the trackbed in heavy haul rail, with an emphasis on how these products protect the subballast capping layer, which plays an important role in the overall trackbed performance. So I'll go over the products individually, and then part two will be Dennis, and he will talk more about field applications, and he will be going over 3 different scenarios that the rail operators and consultant engineers may encounter. And those are situations where geosynthetics can eliminate the need for capping or box outs altogether, cases where they can significantly reduce excavation requirements, particularly over soft soils, and using geosynthetics in high impact transition zones such as bridge approaches, turnouts, over culverts, and the like. So the first part, very much product focused, and then we're going to switch to actually applications and where it's how they're applied in the field. So as I mentioned, I'll be going over key products and their benefits, and I will get started on that. The focus of my slides is to look at how geosynthetics provide engineers with practical tools to improve and maintain the subballast capping layer. So we look at these individual products as a toolkit, tools in a toolkit, and we'll discuss their benefits, and then later on where they can be applied in the trackbed. And my section will lead into Dennis's section, how these products actually work together as more of a system, which we usually see them in the field. So the four main products, well, the four products I'm going to cover today are that are using the Trackbed are large aperture multi-axle geogrids, which are typically installed at the ballast and capping interface, and they function. Their function is ballast stabilization. Then we're going to talk about Trackbeds, which is also installed at the ballast capping interface underneath the geogrid, and that functions to provide capping protection and moisture control. Then a little bit further down the Trackbed, we're going to consider OmniWeb, which is a type of geocell, and this is used in the subballast capping layer itself for reinforcement. And then underneath the geocell, we're going to discuss briefly Marathon H2RX, which is used directly on the subgrade and provides additional reinforcement. So I thought I'd include this slide and this photograph because it's actually, it kind of sums up what we're going to talk about. So obviously we've got the individual products that we're looking at, but really they come into their own when they work as a system. This photograph, I took this photograph in Port Hedland on a project where the rail operator was having some issues with the formation, track geometry issues, but there was a lot of and that was due to a soft subgrade formation. It was in a tidal zone, so the water would come in and affect the capping layer in particular, and it would get washed out. So they were looking at ways to reinforce this Trackbed, and we've got, you can see here, the different layers. So just underneath the ballast here, we've got, you can't see the geogrid, but there's a tensile geogrid and Tracktex underneath the ballast, sitting on top of the capping, and then the capping layer is reinforced with a geocell, which is OmniWeb, and then underneath you can see the Marathon high strength woven products, which would be H2RX at the moment. So that just kind of gives you a good overall of the products working as a system. As I mentioned, I'll just briefly go through each product individually. I think it's important to understand what the product looks like, how it works, and what benefit it brings to a capping layer. Some people have heard the words thrown around like geogrids and geotextiles and this, that, and the other, but don't always know what they actually look like. So we'll cover that before Dennis goes into his section and talks more about the geotechnical parts of the products. So the first product, as I mentioned, which is used to stabilize the ballast and goes directly under the ballast, is a large aperture geogrid. We've been supplying triaxial geogrids into the Pilbara for many years now with a lot of success. These are delivered to site in rolls, so they're loaded onto a semi-trailer, taken up to site, stored somewhere, and they're ready to be deployed on when the guys on the site are ready to do that. It's just a couple of photographs just to demonstrate geogrid being laid out. Very quick, very easy. It doesn't take long at all. And then after the geogrid's laid out, then they come along with the ballast. Typically a front end loader will spread that over the geogrid. So I think it's important just to briefly understand how ballast stabilization works and how geogrids create ballast stabilization, because that will help us understand how they actually benefit the capping layer. So as I mentioned, we supply large aperture multi-axle geogrids, typically TX190L. The apertures are actually designed, they're larger in size than other geogrids, and they better fit a ballast particle size, which is around the 60 mil diameter mark. So the large apertures, they'll nestle into the apertures and interlock with the geogrid, and this basically, the interlock reduces lateral spread of the ballast particles and confines them in place. This confinement increases the ballast stiffness and its shear strength. and basically these mechanisms collectively stabilize the ballast layer. So how does this fit in, and how does this benefit the subballast capping? It has two major benefits. The first benefit is it protects and preserves the subballast capping. It does that by spreading loads more evenly across the subballast capping. This in turn reduces the pressure and shear stresses on the subballast capping, and it minimises wear and softening of the capping layer. And this will help retain and sometimes even improve the performance of the subballast capping. And this point here, Dennis will touch on this a bit later. It can also, in some cases, the rail operators can use existing non-compliant but marginal subballast capping material. It can be retained, and you may not need to actually dig it out and replace it. So there are benefits in that aspect. And it protects the subballast capping in high impact zones, transition zones. You typically get high loads coming in with impact load spikes at the transition points, which can degrade the ballast, and this can put a lot of extra additional stress on the subballast capping itself. So that's where that ballast stabilisation fits in, with benefiting the subballast capping layer. So now on to Tracktex. Tracktex is a geocomposite product. It's basically, there's a microporous filter that's sandwiched in between two heavy grades of bitum non-woven geotextile. It's installed directly under the ballast, and typically sometimes under the geogrid, and this helps protect the capping layer and also can help control moisture at the formation and capping level. Again, these are delivered to site in rolls, so easy logistics, very much similar to geogrids. Again, very much similar to geogrids, they're easily installed, rolled out on site. They are actually heavier rolls. Not that this makes much difference, but you might need to move them around with the prongs of a front end loader rather than the guys actually just putting them, over their shoulder and carrying them around. But other than that, very easy to roll out. I think it's important to mention about the actual physical characteristics of this product, because it kind of lends itself to how it provides its benefits. It has two very heavy bitum geotextile layers. So they're bitum A74, and combined grams per square meter of 1,300 grams per square meter. And this acts as a thick cushion, effectively. And then we have the microporous filter, which is in the middle of this, and this can filter particles down to very fine particles, and it's designed to retain even clay fines down to 5 microns. So it holds back a lot of the fine material that you'll find in the subgrade area. It's important to note that the A74 itself, although it does filter, it's better suited to coarser fines, typically fine sands, because the pore size of bitum is quite a lot more, as you can see, than the microporous filter. So bitum alone won't hold back clay fines that you'll find. So if there's any subgrade mud pumping issues, in the past, rail operators have tried using bitum to solve that problem, but the clay still pumps through. So you really do need the microporous filter in those type of situations. Just move that up there. So how does it work? Pretty simple, really. As said, it's got the filter in between the two layers of geotextile. The filter, for all intents and purposes, is impermeable to rainfall. So under atmospheric conditions, so just rain coming down, that won't infiltrate through Tracktex. And if you grade your formation and trackbed, in a correct way, then you can laterally drain off water off of your trackbed and formation. But importantly, it does allow the passage of liquid to go up and through under dynamic load. So you don't want an impermeable layer that just traps your water and moisture underneath in your formation subgrade and for it not to have anywhere to go. So whilst it doesn't allow rainwater to go through from the top, it does allow any pore pressure and moisture to release through the microporous filter. So how does this benefit the subballast capping layer? Well, first and foremost, it keeps it dry. So you're going to have it dry because the rainwater can't get in from the top, and then any trapped moisture can get out. So then it gives it a chance to dry out, and this helps maintain its unsoaked material strength, basically. So a capping layer, subgrade formation layers, materials, when they're dry, they often perform better when they're at their strongest. So it gives the formation a better chance to retain its unsoaked material properties. So just the key message going on from that, Trackbed helps to control moisture above and below the subballast capping. And as I mentioned, the thick cushion layer provides a beneficial function as it minimises any grinding of the capping layer from the ballast itself. So it will prevent the fines being generated in the capping, which can lose. If it gets grinded away, the capping layer may lose its mechanical properties and strength. And with the fine generation, any moisture and rainfall can potentially turn that into a bit of a muddy slurry, and so you don't want that. So it actually helps prevent any damage to the capping layer itself. Onto the OmniWeb. So OmniWeb, the first two products were installed on top of the capping under the ballast, and OmniWeb is used to reinforce the subballast capping itself. It actually forms part of that layer. OmniWeb is it's a type of geocell, and its job is to fully confine, reinforce, and stiffen the capping layer itself. It's actually comes in panels, and these panels are expanded on site to the width of the box out or excavation, and the subballast capping then is brought in and tipped into the cells and then spread and compacted. These are delivered to site on pallets, so a little bit different. They don't come in rolls like Tracktex and TX190L. They come in pallets, but again, they're very efficient to get up to site and store and move around. So no problems there. Just the quick a couple of photographs. So here's a GeoWeb installation, and basically, just a quick note: we previously used a product called GeoWeb, but we now use OmniWeb, and it's the same product, other than the OmniWeb is wider. So it's gone from 2.5 meter wide to 5 meter wide panel widths, so which better suit typical box out widths that are around 4 to 5 meters wide. So you don't actually need to connect the GeoWeb in the middle anymore with the OmniWeb product. Typically, the cell depth is 150 mil, and the capping will be poured in, and then you'll have an overburden amount of material of about 50 mil. So your box out is around the 200 mil thick mark and about 4 or 5 meters wide. And as I said, it's just the capping material is tipped inside. The limiting factor, so OmniWeb is extremely quick to install. You expand the panels widthways and lengthways, and then you join them with the Atra keys end to end. That really doesn't take very long. The limiting factor for installation is how quickly they can pour the capping material itself. But generally, it isn't really much any slower than if they were just putting down capping alone. It might be a little bit slower, but not much really. And then you're going to compact it in the same way you would do with just a normal subballast capping. Again, I just want to explain how it works, so you understand how it will benefit the capping layer. Vertical loads are transferred into the geocell, where the confined infill attempts to spread laterally. But the cell walls themselves, they prevent this the movement of the capping moving outwards through frictional resistance between the infill and the cell itself. So there's friction here along the depth of the cell. Hoop stretches are created when the load comes down, which prevents expansion of the cells, and there's a passive resistance from the neighbouring cells as well. So these all work part of a unified system in confining this each individual cell, the material in each individual cell, and you'll get an overall stiffer, stronger layer, basically. So pretty much what I'm saying here. So together they confine and stiffen and reinforce the layer, this layer here. So what benefits does this provide? So this will actually provide benefits not just with the subballast capping layer, but also the ballast itself and the subgrade underneath. Cellular confinement will create a semi-rigid slab effect, which will provide a uniform platform for the ballast to lay on, a strong uniform platform for the ballast to stay on. It spreads the loads wider and shallower, so it's quite a good image here. Without the GeoWeb, you're probably going to see a bulb that goes a lot deeper and narrower, so you're going to have a lot more stress, particularly at this point on the subgrade itself, but the GeoWeb will spread that over a wider load and shallower. So this allows GeoWeb to be and subballast cappings to be installed directly on weak and soft subgrades, and a major benefit which we're seeing all the time is in that case we can have reduced box out depths. So rather than over a soft subgrade, rather than going down 500 millimeters without bit reinforcement, we can save 300 mil and go to 200 mil when there's many benefits. Dennis will touch on this in his section a bit later, and this smooths and stiffens transitions at high impact zones as well. So again, Dennis will touch on that in his section. So the last product I just want to briefly talk about is Merathi H2RX, which is a high modulus, very stiff, moisture managing reinforcement woven geotextile. And in the context of what we're discussing and trackbed reinforcement and renewals, it's a product that comes in hand with the OmniWeb GSL, and they actually work together really well. We'll just make a mention that previously we've been using a very similar product called RS380i, but now we've moved on to H2RX. They're both products by Solmax, but the H2RX product is basically the same as the RS380i, but it has a moisture managing function with it as well. So there is an additional benefit for this product. Delivered to site in rolls like Trackbeds and the TX190L GeoGrid. And you can see here it's installed directly under the geocell on top of the subgrade. So it's very, very quick and easy. It's similar to Trackbeds and the GeoGrid. So how does it work? It provides three functions. The one, well, they're all pretty important, but to start with, it provides reinforcement, and it does help to increase the stiffness of the GSL reinforced subballast capping. So although the GSL will increase stiffness, it will be improved by using the high tensile strength Merathi H2RX product underneath with high strength but low strain, and that will help minimize any deformation at the subgrade capping layer interface even more than just the GSL alone. And it also, another maybe underrated function is the separation function. So it ensures that the subgrade fines or material doesn't ever intermix with your subballast capping that's infill that's in the geocell itself. So you're literally going to be keeping those two materials, subgrade and capping, separate. There's no way they're going to mix, or over time the infill of the geocell making its way into the subgrade or vice versa. So that's they're the two major functions. And with the H2RX, this actually has a moisture management function, which I believe is going to play a key role in keeping the formation and capping layer dry, alongside with the Trackbeds. So the basically is designed to wick water from the subgrade. It can also wick it down from any moisture above, and it will wick it towards the product and through capillary action, and that is then moved sideways to the sides of the product through this wicking mechanism. So you're going to be drawing moisture out from the subgrade, moisture from below, and get it out of that interface. So you can imagine with Tracktex on top, keeping the rainwater off and draining it to the side, and the H2RX underneath, draining it to the side, you're going to have a nice, dry, strong, stable capping layer and formation for a lot longer than you would do potentially without these products. It is worth noting, and I do need to just confirm this with the tech guys at Solmax, but the wicking in a rail trackbed application will only really work if it's the formation, which is the or the underside of the capping layer is above ground level, because the edges of the H2RX need to be daylighted to allow that moisture that's wicked up into it to release out and drain away. Otherwise, it'll have nowhere to go if it's installed under the ground. So you're going to need it. It would be ideal in embankments or where the formation is at grade or the same level as the natural ground. But we can see a lot of benefits of this product for sure in helping to maintain the overall trackbed material strength. So just to summarise, before I pass you over to Dennis, a key message is I want to just get across is geosynthetics act as tools to protect, reinforce and control moisture within the subballast capping. Together, these functions enhance the capping performance, improve its ability to support the ballast subgrade, and basically strengthens the overall trackbed resilience. So I'm going to pass you over to Dennis now. He's going to be talking about, it's going to be more of a practical discussion, and he's going to look at selecting the right geosynthetic system for different trackbed scenarios. So thanks for listening to my section. Dennis? Dennis, do you want to unmute yourself?
Hi, everybody. Thank you, Matt.
Okay.
So I'm going to start looking at my section. So obviously we started looking at various treatments that you can do to address poorly, marginal or poor formation that might be present particularly from older historical constructions. And so we developed a range of solutions that we can use to go for that. So if we look here. So in the typical problems that we have, with marginal formations, non-conforming subballast capping or subgrade, potentially no capping layer in some cases, weak, soft subgrade, clays, over east it might be the black cotton soils, or in the Pilbara, your Gilgai formations is obviously quite a range of those. Localized bog holes, mud pumping, fouled ballast and all that sort of stuff. So, what are the operational impacts of that? Is basically, it leads to speed restrictions and downtime, frequent maintenance work, and overall loss of revenue for asset owners, which, is the key thing that we're trying to avoid. Here's an example of a bog hole. So in the formation here, there's a bog hole and mud pumping occurring here, and further up the track, there's a few spots through here. We've undertaken a test pit on the side of it and identified, and you can see there very clearly, your edge of your ballast, your sleepers and your ballast is, extremely fouled, completely fouled, and materials moving from this marginal subgrade up, probably, what do you call it, ballast pockets forming there, and localized water ponding, and it's just not working very well. So, so basically what the traditional method to fix that is dig out the weak and crappy material and backfill it with good material. And we looked at these situations, and we thought, well, how can we reduce the volume of excavation and downtime, and enable just a quicker formation replacement. The overall idea of our work is to look at what are the geomechanical behaviors of the subgrade and subballast capping, and how do we rectify those effects with the geosynthetics. As the design process, we obviously identify where there's poor track performance, so do some investigations, and then those investigations define what are the marginal or poor characteristics of the formation, and then go through a process of designing applications to address those performances. And it's important to sort of note that we don't need the perfect solution, and we need to accommodate variable ground conditions, because obviously with geotech investigations or anything we do, there's variability along the track. So how do we minimize the effects of those? After we've collected all the data, done testing and analysis, the analysis component, we look at what are the design tools we've got. We look at the bearing pressure for weaker soils, Kentrack and Plaxis or other finer element analysis programs to see how the stress is being applied and what effect that has on service life of the operation. How does that compare to a traditional solution of digging it out, backfilling it with compliant materials? We obviously use, in doing those analysis and defining our parameters and so forth, we look at research that's been done, and that can be down to individual tests or published papers, published information from the manufacturers, but also we looked at full scale trials which were done in the States, particularly for softer clays, and then that's led into when we've applied it in Australia. How does it actually perform? And we've seen over the last sort of 6 or 7 years a very good correlation between what we're expecting and what's actually occurred. Here's some examples of the different treatments and supporting what Matt showed previously. So this one here would be a bridge. This is a bridge here. The cross girders, metal cross girders, ballast. We've cleaned it out. Then we've put this geocell solution in here, backfilling it here, and that provides a stiffness transition from your very stiff bridge to your relatively moderate stiffness here, and then lower stiffness where beyond the geogrid solution. This is a solution of a non where we haven't dug out the poor material. We've just installed the Tracktex and geogrid on top of the formation, which is a marginal formation. So we're looking at 3 cases, and the first case is basically where we want to eliminate excavation. So that's the solution where you've got marginal subballast capping and subgrade, and it might have a marginally weak or marginal high plasticity, or there's similar sort of situations like that. And in that case, we're looking at installing the Tracktex directly on top of the subballast capping, and then the geogrid. The reason we do that is, well, each item will depend on what the characteristics of the formation are that we've defined in the investigation. And but if we've got weaker subballast capping and subgrade, then the Tracktex provides the water management so that we don't get it doesn't go to the unsoaked condition in a traditional sense, and then so we can apply or assume unsoaked or partially soaked conditions during the design process. So this cross section here is a good example of what we're doing here. So traditionally, you've got your subgrade, your capping layer that may or may not be the same as your subgrade. And then what we do is we look at the track text goes on the bottom directly on top of the capping once you've reformed the geometry so that any water that falls on it's going to go to the side and get off the track, and then the geogrid on top. So that basically just allows where you've got the marginal conditions. Here's an example of that, where you're just directly placed on top. So this sort of solution has successfully been applied in heavy haul rail applications over 100 kilometers of track. So it's over a number of years, with several 100 million gross tons per annum. So that's it's a pretty good record for that process. The next case we look at is the reduced excavation. So this is where you got formation that's worse than, you can't say it's marginal. It's actually, very soft or soft, and they might have reactive clays there, or you might have moisture sensitive material. You might have bog holes, mud pumping, wet spots, that sort of thing. And traditionally you'd dig out the subballast capping and possibly some of the subgrade, and then backfill it with conforming materials. So this treatment looks to use the geocell on the base. So the solution, we dig out the 200 mils or so. We install the Marathi on the bottom to prevent the fines migrating up into the subballast capping and to distribute the loads a bit further. The geocell goes in, as Matt said, to distribute loads over a much greater area. And then that gets backfilled with subballast capping, and then the Tracktex goes on top. So this is a good solution for where you've got weaker soils, your subgrade particularly, and you might be concerned if you dig out and just replace the subballast capping, it might end up just deforming and degrading into the low strength subgrade, when it gets wet. Here's an example of that solution being applied at a turnout. So you can see dug out a little bit, install the Marathi, and then install your GeoWeb, backfill it with your compliant subballast capping, and then you trim it to the grade, and install your Tracktex. The third case is similar to the previous case, but where you've got high dynamic loads or high changes in stiffness across a structure, and it's very similar in terms of the geosynthetics used, but we add in there the geocell. Sorry, not the geocell, the geogrid, the TX190L, so that it's just adding that extra bit of transition over the stiffer structure. So in this case, it's exactly the same as the previous one, but you've got the geogrid on top. So the key here is trying to provide a stiffness transition, particularly over, say, a bridge or other structure, and where you've got very high stiffness on the bridge, and then trying to make it moderate over a short zone, 20, 25 meters beyond the bridge, and then onto the formation embankment. And this treatment's worked very well as well. It's been applied in Australia, and it's a go-to system for a couple of the railway. When they're doing their renewals on bridges, they apply it as a standard. So here's an example of that on the bridge. This is the case before it's in there, and all rail's been taken off, and then this is sort of showing how it extends up to it and abuts against the bridge, and then the ballast gets backfilled in here and so forth. So the key thing here is it stops that traditional dip you get at a bridge interface. As I was saying, it's been applied in numerous bridges, rail bridges, and successfully. So here's some more examples of that being applied. What can we see in here? Just some pretty pictures, really. So, but you can see that it's. I guess this one shows the full case of it, of the geocell backfill, compact it, trim it to the grade, and then install your TrackTex and then your TX190L. So the summary of these applications. So the no excavation solution, it's where you got your marginal formation. It's quick, it's low disruption. The second one, the reduced excavation system, is incorporating your Merapi and your GeoGrid and a GeoCell, and it significantly reduces the amount of box out or formation replacement you need to do. In some of the cases we've looked at, we've reduced from 600 or 800 mil depths of box out to 250 mils, and it's particularly important where you've got, say, two close track centers, dual track close track centers, and you've got a deep excavation next to a operating rail. Obviously there's considerations or concerns for instability of that track in the short term while you've got it open before you've backfilled. The transition zone, case 3, was trying to manage that stiffness transition and getting the full body. One of the things I'll sort of highlight is that these 2 bullet points at the bottom. We want to assign the treatment based on the geotechnical behavior that's missing from the existing formation. We're not just sort of saying chuck these materials in and hope for the best. We're actually looking at, scientifically looking at it and saying, well, these characteristics are missing, so therefore these materials are required or can be applied, not are required. The other thing is we like to align the treatments with the client requirements and their renewal strategy. So it's not just a standard design that comes off the shelf. We actually align it with discussing with clients and how individually how that applies to their implementing it. In terms of shut duration and impacts on operations. One of the things before I go to this slide, one of the things that some people are concerned about is the presence of geosynthetics at the base of the ballast layer, and because people are concerned that if you're going to go along and do some ballast cleaning at some future point, is that going to impact it? And of course, yes, it is. Is it going to get impacted when you're doing your tamping and so forth? But in terms of that, we can manage those risks, and in some cases we'll eliminate the materials at the top of the formation, just so that we can eliminate that legacy issue. But in most cases you can manage the ongoing maintenance of those impacts. So here's just a bit of a blurb for my company. So we just look at undertaking renewals from the ground up, and looking at excuse the pun, and investigate, define what's actually missing from the geotechnically, what are the characteristics that we need in the different layers, whether it's your subgrade attrition or your strength, your service life, your other various things. We optimize the formation treatments for each individual case. We can apply independent verification for other people doing similar work, and we like to apply our treatments based on testing, published information, research, and also practical application, in the field. So how have they actually worked, and how do they go? And we've got a good record of applying these treatments over 7 or 8 years, and on heavy haul rails. So that's the end of what I was going to talk about. But I was just going to, if anyone's got any questions, we'll go through those now.
Thanks for that, Dennis. Thanks for sharing your knowledge with us all. I'll just have a look. Can't see any questions, which is pretty surprising because we usually get a few questions at the moment. Is anyone got any questions that they would like to ask Dennis while we have him?
What do they just put them in the chat messages?
Unless it's just not showing up on mine. It's I've gone on the Q&A and no open questions at the moment. We might get away lightly here, Dennis. We'll wait a little longer, but yeah. So as I mentioned at the beginning, this has been recorded, so it can be reviewed again at a later date and shared around with your colleagues or anyone that's interested. I don't think so, Dennis. So, oh, here we go. For the Trackbed, so I've got a question here for the Trackbed. How will it work for not allowing the rain pass through, but allow the moisture from under? I think I understand, and it kind of goes to what I was saying earlier on the Trackbed, that the micropores filter is been designed and tested to allow the water to rainfall and any water under atmospheric pressure. It won't be able to go through it because the pore size is so small. So it's very much impermeable for rainfall, but under dynamic load, those pores, so any moisture under the subgrade or under the formation and capping, those the pores of the woven microporous filter, they actually open up, and the moisture is driven up through the pores of the filter. So it does need some force and dynamic load from the train above to create that force to allow the water to release through the pores upwards through the filter itself. But when there's no force, those pores are so small that any rainwater that falls down on them, that will just drain off laterally. I hope that makes sense in terms of how that works, the mechanism of that.
Sorry, yeah, that's right, Matt. An analogy that's been explained to me of how the system works is akin to a rain jacket, a raincoat, where water will fall on it, bead, and then fall off, and then but moisture from your body will wick through, and it passes through because of that. But it's not exactly the right analogy, but it allows moisture to wick through, but it won't let the rainfall come through. It's similar to that.
Thanks for the question there. Much appreciated. We'll wait a little longer, see if anyone's got any other questions. No, I don't think so. So we'll wrap up now, Dennis. I just want to say thanks again for joining and sharing your knowledge. And if anyone wants to reach out to myself or Dennis, if you've got any projects you're working on or you've got any technical questions that you want to ask behind the scenes, feel free. Both of us will be available to assist where we can. And yeah, okie dokie. All right, then I think we'll end the webinar. So once again, thanks everyone for joining, and thanks Dennis, and we'll see you all again soon.
Okay, thanks, mate.
Cheers.
Thanks, everybody.
Cheers. Bye
Bye.
bye.